So what I've decided is that so we will be doing scattering today, like pretty much the idea of why is the sky blue, like what comes out of it. That's what we will do. But the homework, I don't know how to put it. I would have liked to post the homework last week and then or do this last week and make it due this week. So what I'm thinking of is that most of this homework will constitute your final exam, and then I will ask one question, just a relatively simple question, which will be about 25% of your grade, which will be from anywhere from the semester. So you have to work for it, and by anywhere I mean there's mostly the homework and some part of the homework, very tiny part of the homework. For example, somewhere you're taking basically you jump, fill in the steps, right? That is, and unless you carefully attend to that, you can miss something. So something that is really needing a little bit of care. Simple, but if you could have missed that. So that will make you guys go through the whole of the course, and there is a homework also associated, which is 80% of the. Is that reasonable? Okay, so that will be a final exam, which will have 80% take home, and take home will be available to you in the next couple of days, probably by tomorrow. But it is due at the time of the exam. 80% of it is due at the time. Is that very clear? Yeah. Okay, we want to talk about electromagnetic scattering. It broadly is the same as, it's a slight generalization of what we have already did. What we have done is, if you give me a current like radiation, right? So radiation involves. So there is a source somewhere here. So that's your R prime, and that's your and in the approximation where R is large compared to R prime, we were able to get the fields and the power and pretty much whatever was needed, we could get. What scattering does is, and this is pretty much charged. I had to make this, there are a collection of charges. If I make them move, accelerate, basically they will radiate. Right? That's the idea. But now scattering involves two things. One is I send an electromagnetic wave, which is basically oscillations in electric field. And there is a dipole, induced dipole moment. There are particles that can induce dipole moments. Like think of water molecule. Electric field comes here, it oscillates the water molecule there, which has a dipole moment. It induces, first of all, it has to induce a dipole moment, and then it oscillates it, and again it radiates. So this oscillates, and then it's radiates. So scattering involves an incident electric field. So that is a E incident, and this we will call it the E scattered. So the scattered field and an incident field will be there. So incident field comes in, disturbs the material, creates a dielectric function, and that radiates. Or I shouldn't say creates a dielectric function. The dielectric function properties of the material decides the polarization that will be induced, and that polarization, if it has the time dependence, that causes scattering. So that's a simple idea, but now we have to write we have to go back to Maxwell's equation and do some changes to it so that we can use the results from here inside in here with this incident. So we have to prepare our Maxwell's equation, or re-prepare in a sense, do some basic changes. So let's go back to our Maxwell's equations. We have Maxwell's equations are charted with D of R comma T is equal to charge density. I don't want to keep any charge density. So let me suggest what we are trying to say here. So maybe, I think if you remember your electrostatics, that is this epsilon naught times E is equal to rho. So that's if the material has charge density in it. If you have a permanent polarization, that is dotted with P. So this is permanent polarization. Think of water molecule. Water molecule has a permanent dipole moment. And you can also have an induced dipole moment. So that's dotted with P induced. Induced dipole moment means that you need an electric field for this to work out. And how that works is that induced dipole moment, let's say R comma T, is equal to E cube prime, sorry, E T, it's in time. It can be R also, but say there are local interactions, so that is dt prime, and the susceptibility of the material comes into picture. So that's R and T minus T prime dotted with epsilon naught times electric field. Okay, but this is a disturbance. This is a response if you want. There is no induced dipole moment to begin with, but if you have an electric field, the material can get polarized. So there are charges, positive and negative charges. If you put an electric field, positive and negative charges can get polarized, like typically you say. So there is a material that is positive, negative, positive, negative. If I put an electric field in it, they all can align themselves, right? So that's the idea. This is in time space. If I write this in frequency space, in going back in the last semester, the integral, and I should be careful that this is minus infinity to t. You cannot go beyond t because that will violate causality. A disturbance, an induced disturbance, cannot get its source from the future. Right? It has to be from the past, so that is the limit. And in the frequency space, this is r comma omega times epsilon naught e r of omega. And then you ask, where is the causality involved in here in the frequency space? There we say that this has to satisfy Kramer's chronic relation. Right? So we say that chi is causal. For our purposes, we will use this. And since this is algebraic in structure, it is convenient to say that we should write our Maxwell's equations in the frequency space so that we don't have to worry about this integral. So we will, yes.
So in the frequency space, in general, last earlier we did exponential or something.
Correct. You can do that. I mean, exactly that is how you will go from here to there.
Or you just move.
You just moved it from here, and there will be an exponential here. There is an exponential here also, and they will cancel out in such a way that this will work out. And that happens only when there is a t minus t prime dependence. That's a translational symmetry, right? I can move things around. If it was t comma t prime, I will not get this. I will get an integral that then it is a mess. But since this is most of the materials satisfy this, then we can have. So this is called linear materials. Yes.
The exponential in the Fourier series because of the unitary transformation.
No. No.
Because the unitary transformation, we write it like exponential.
Correct. But this is not that. Let me see. Unitary. Okay. So it has all to do with the scalar product. So let us say that is psi times phi, correct? Right? And that is, suppose there is an operator A that acts on psi, and there is another, and the same operator acts on phi. I think that's what it is, right? A times A dagger, if you want, has to be equal to 1. No, that's Hermitian, right? So what is unitarity? So
inverse is equal to transpose.
Yeah, but in this way of seeing it, I think A inverse so U dagger U inverse. Yeah, I think, yeah, sorry, yeah, Hermitianity is this right here. So this is Hermitianity, so this is phi, and that's Hermitian. And unitary is if you have A times psi times A times phi, that's the same. That's in quantum mechanics, it's needed because of the probability conservation. So the answer to your question is it has nothing to do with unitarity, but it shows up as unitarity in quantum mechanics. No, it has nothing to do with unitarity. This one, so the why you see this is okay. A unitary operator can be written, it is possible, not necessary, that it can be written as I times a Hermitian. So that's a theorem if you want. Why? Because if you expand this, U times U dagger, so U dagger is equal to exponential of minus I H dagger, correct? But H dagger, if it is Hermitian, these two are the same. That is e raised to minus I H. Right? So U times U dagger, these two will cancel each other and it is one. So this leads to the idea that U can be written as a Hermitian operator. So that's the reason why you see these exponentials. Here it is, why do we have it here? It's just sine and cosine. So Fourier transform is more like sine and cosine. You're trying to use sine and sine function and cosine function to write something out. That's the way to see it. I don't think the connection is there.
Because the terminology, there is no connection.
Yeah, I don't think so. Yeah. On the other hand, once you write this, then this is an exponential. Fourier space is very much used or plays an important role in quantum mechanics. But unitarity, probably not. Yeah. Trying to connect. Or keep thinking. Yeah, your thought might be right. I don't want to say that it's, or I'm not seeing it. I think that's the best to say.
I mean, unitarity is a similarity transformation.
No, I don't think so. Let's see. So no, similarity transformation is more general, I think. Unitarity is a special, yeah. So okay, so similarity transformation is S times an operator, a matrix, let's say, right? S times S inverse. This makes a dagger. But U, let's say, even if it is Hamiltonian, U times unitary operator acting on a U inverse, it evolves it. So this will evolve. Right? So this is A prime. So this will evolve that operator, but not necessarily dagger. So, but you can always, there exists a unity operator which is a similarity transformation, but it's not one-to-one. So that's yeah, I think so. Because this doesn't have to be diagonal. Yeah. Yeah. Okay, so we have this, and now we want to talk about a system. So as we said, we will have a incident wave coming in, it interacts with the source and it emits. Now I have a choice in selecting this source. I'm going to select this source as it having no charges, right? And it doesn't even have a permanent dipole. Okay. So it should have no dipoles. Now, if it has dipoles, then it changes things a little bit, and it is still not very dominant because it won't oscillate. Right? It should have an oscillating dipole only then. So still, whatever we consider will be applicable to most of the molecules around. These will be molecules. Think of air molecules, right? These will be the air molecules, like a nitrogen or oxygen molecule there that gets oscillated there. So main contribution comes from here, and this P induced is getting contribution from the electric field. You put this on the left-hand side, and you say that del dotted with epsilon naught E plus, this is chi. So this is chi times epsilon naught E is equal to 0. And what is this equal to? This is a familiar thing. It is written in a very complicated form. What's the definition usually?
Induced polarization.
No, D, right? The displacement vector. So this is written in a very complicated way. So remember, chi is basically epsilon over epsilon naught minus 1. So if I were to add these two quantities, so chi naught plus chi naught times chi, or epsilon naught plus epsilon naught times chi. So this is 1, let us say. So I have to have a matrix in here. So that's the same as epsilon, right? And it is about me. So this whole thing is nothing but epsilon naught E plus chi dotted with epsilon naught E is equal to the dielectric function of the material dotted with electric field. And that's equal to D, right? Okay. So we should ask, where is our source sitting? So this source, I have to realize where in my Maxwell's equation is the information about this. That's inside this D. D has the epsilon naught in it, right? So that's my source. So go back to Maxwell's equation. We have del with D or omega is equal to 0, right? That's, we are not having any charges or currents now. And the second Maxwell's equation is del cross E, Fourier space or frequency space, let's say. Position is still B or omega. Then we have del cross or del dot with E, right? And del crossed with H is equal to minus I omega times D. And there is no J because there is no current. We are not talking about that. I'm talking about situations where there is no current. This is like an air molecule, there are no currents. Okay. So that's our equation. Let's combine the second and fourth equation. Remember, B is mu naught times H. Right? So del crossed with E is equal to I omega mu naught times del crossed with H. But del crossed with H is equal to I omega mu naught minus I omega times D. Minus minus goes away, minus and I square goes away. So there's an omega square. And let me write this omega square over C square. Mu naught is there, so I multiply and divide by epsilon naught. So 1 over epsilon naught times D. That's my equation. So this is going to be our primary equation. Let's rewrite it a little bit. So actually, write it here. So D is epsilon, right? So that's your epsilon. So let me write that as omega square over C square. This is epsilon over epsilon naught times E dot with E. This is on the source. So this is actually the source, but I would like to point out that even in the absence of the source, it is epsilon naught. So there is some part of it which is not really the source, which is in the absence also. So let's subtract that out completely. So let me add and subtract a -1 there. So let me do that here. Next page. So I have del cross E. It is R omega. That's equal to omega squared over C squared. I want to pull out the source part separately. So I say this is epsilon over epsilon naught minus 1. I'm adding and subtracting there. So, and then I say this is plus 1. So plus 1, take it on to the left there and read this as, so this is nothing but chi naught, epsilon naught times chi. So overall, what we have is L cross del cross E, or pull this piece to the left, so that's minus omega squared over C squared times 1 times E is E itself. And that's equal to omega squared over C squared times chi with epsilon naught and E. So this is the source, right? If there was no disturbance, then if chi was 0, this goes away, and that's your free signal. If this was not oscillating, then that's what is the left hand side. On the right hand side is a source of scattering, if you want. So somewhere it gets activated, then that gets a contribution. Let's rewrite this a little bit. Let me write this as C squared over omega on this side, so that completely source is on the left, no frequency dependence, and electric field can be taken out. So this can be written as C squared over omega squared. So these two goes away. And let me write this as L cross. I want to take an electric field out, but then something has to sit there, so I replace that with 1. That's my equation, and this is minus. I'm going to take the electric field out, so I replace it with 1 and dot. This is chi or omega epsilon naught E. Is the quantity inside the bracket a scalar, a vector, or a tensor? It's a tensor because this is a tensor, right? Pick one term and that decides the nature of the quantity. This is a tensor. So this seems like a triple product, but there is a 1 here. So first, like one side of that unity forms a vector, and still there is one more vector. So this is a tensor, right? Or a dyadic. So a matrix multiplies a vector, matrix multiplies a vector, or a tensor multiplies a vector. So that's what it is. It might seem a little odd that there is this electric field that you're looking for, right? So main idea is to solve for the electric field here, but the electric field is a source also. So it is not yet in the right form, because we would like to separate these two, right? There is a scattering and an incident wave. Incident wave affects the source, and then there is a scattering. So that's not really taken care of at this point, because here this electric field is there on both sides. So we have to bring this as a boundary condition, right? That electric field can be broken into 2 pieces. There is an incident and there is a scattered electric field. Question.
The epsilon naught on the right hand side, like 2 lines above that where you have epsilon chi.
Mhm.
On the top right of your left board, you don't have the epsilon out there. I'm just kind of confused where that is coming.
Oh, where did that come from? Oh, oh yeah. So this is the definition, right? I replace this with this. Oh, I meant to write this as right chi. Yeah, D. Right? So D has epsilon. Epsilon, if I were to replace this, that is a chi naught E, and this chi is. Oh, so you're saying it's not that now, it's that. Okay, help again. So epsilon over epsilon naught. So this is just chi or something, right?
Mm-hmm.
Probably. Okay. So that's just chi. And then there is chi dotted with just an E. Well, that's just E, right? And chi dotted with E is a P. Yeah, polarization is the source, right? I think that's all there is to it. Yeah, I think this is, there is no epsilon naught. I can check. Got my notes today. Yeah, I think it's correct. Yeah. Okay, thank you. Yeah, okay. But we still need to process this because there is an electric field on both sides at this point, and it's not ready for our to put it into the configuration we are interested in. There's one thing we can do, and that is, let's rewrite this a little bit. This is a cross product, right? So I can, so this is A cross B cross C, that is B survives and then there is 1. So notice that del cross 1, it's a dyadic, that's equal to this is the main thing, and then there is del dotted with 1 and minus of that survives, and that is the del square of 1. Correct. This is anything operated with 1 is gives you that quantity itself. So this is a tensor of this time. There is a gradient square operator, and there is a gradient. Right. So if I were to write it in that form, I get C square over omega square, and then this as gradient minus of C square over omega square gradient square times 1, and then that is minus 1. That's just like rewriting basically here. Dotted with electric field is equal to chi dotted with the electric. I'm going to write that as pull this c square over omega square out. Write this as gradient, gradient. I pull this out, that is a minus, let's say 1. Also be pulled out. And whatever is remaining is del square plus omega square over c square times electric field. And this way of writing has this advantage that this piece here, this tiny Green's function that's shifting here, that's our radiation Green's function in the Fourier space. We know the solution for it. Chi dotted with E. So again, this piece here is our old Green's function in the radiation case. So let's define a Green's function. Let's define our Green's. This is called the Green's dyadic. So the Green's dyadic will be defined as, basically it is motivated from this. So you say same operator, except on the right side, there is a delta function. Since it's a dyadic, you say this is now a matrix or a tensor if you want, and 0 just means that it's a free Green's function. In principle, you can add quantities to it. This is R prime, remember we have omega, and this is delta function. Just so that we have this omega square over c square, I think I define it. No, so this is with c square. Yeah, this is with c square over omega square. I define. And since it's a dyadic on the left, I should have a unit matrix on the right. Is that clear? It's just a more elaborate Green's function, but we will see that for our purposes, it is only this piece that is going to contribute. So all this will collapse. This is very general at this point. I haven't used the far field approximation yet. In the far field approximation, all these gradients become stay hat. Okay. Any questions as such? Okay. Yes.
That's a gamma function.
Not a. So this is Green's dyadic. This is the Green's dyadic.
Oh.
So basically, this is the inverse operator of this pole operator. If I can solve this equation, I can do any problem in electrodynamics. Right? Give me any material, I solve for the electric field, right? And this can be used to solve it. But we will be interested in a smaller problem where this is very far away. And in our far away regime, basically the idea is that the gradient can be replaced by k, the vector k. So the main point will be in the far field approximation, this can be replaced as I times k, where k is equal to I times omega over c times r hat, so observation point, right? In the far field approximation, this is nothing but the k itself with omega over c taking over. So to see that, how do you know that that actually helps us? Let's do one more step. If I take the gradient here, if I were to take the gradient operator at this point, it is clear that, so take a gradient operator here and take a dot product. If I take a dot product there, this becomes del square, right? Laplacian. There's already a Laplacian there. One with the gradient operator becomes a gradient. And in that case, these two terms cancel out. Right? If I take this, these two terms cancel out. And if that two terms cancel out, there is only this piece contributing. Omega square cancels out. This is 1. So it's the divergence of the, Green's dyadic is equal to the divergence of the delta function. I can go back and put this back in here. So there is a divergence of the dyadic sitting in there. Take it onto the left hand side because now they are delta functions. So this takes the form equation.
You're taking the dot product of the whole thing?
Of the whole equation. Yeah.
Okay.
So this gives you a del square. In that case, these two terms cancel out. That's observation. And this piece here is a divergence. That's all survives. And since I've taken a divergence everywhere, I should take it on the right side also. Okay, so I learned that divergence of the Green's dyadic is a divergence of a delta or function. Which then put it back in here, remove the divergence there. Now, this is meaning that, so the first term here is c square over omega square times the gradient. This is the divergence of the Green's dyadic, which is nothing but the divergence of the delta function. Delta function, we do it symbolically, that's minus 1 times L square plus omega square over c square dotted with gamma naught is equal to 1 times delta function. I have not put in the r minus r prime dependence in the delta function. And I've used this fact that this dotted with this, that divergence is equal to this. Okay, is that clear?
Can you explain how you do it?
This piece here has a divergence on this. That's this. So I put this in front here. Is that clear?
Yeah.
Okay. That allows me to take this to the right hand side, all the delta functions on the right hand side, and there is a c square. I should have also written the c square over omega square, right? So that's c square over omega square. So multiply it out. So I have this equation del square plus omega square over c square times the Green's dyadic is equal to, so I've killed the omega square c square, comes on the right, and this is minus gradient plus omega square over c square times 1 delta function. Is that clear? Sure. Some Simon. Simon. Oh, apparently this is minus sign. Why is this a minus sign? Did I miss something? Oh yeah, because this minus, these two cancel out. And this minus sign hits this, right? So this is a minus sign. So this is clear? As minus sign. So this is the term that survives. Because these two terms cancel out. This term survives as minus sign in the front. That's a minus sign, and then when I replace that, there will be this minus sign. And then this minus sign is not there. But that makes it very easy because we know the Green's function associated with this operator. Remember that L squared plus omega square over c square. We called it the Green's function, just G R, comma R prime omega is equal to delta function. So if I know this, I can solve for this then. And what was the expression for G? G was equal to prime was equal to 4 pi and R minus R prime. As far as position was going, it was a point short, but the frequency dependence was there in the exponential. So exponential I omega over C 3 and the R minus R prime. Remember, right? That was our. So I know what this is. I just have to put this back in here, right? So it will be the inverse of that. So that seems to tell me that if I were to operate this from the left by gradient, so this seems to tell that the gradient, the dyadic, Green's dyadic is actually equal. So I just have to operate this on the left, right? So if I put this on the left, put it from this also, and then that's my G, right? So this will be divergence omega square over c square times 1 times my Green's function. And in this context, let's call it, since there is a 0 sitting there, so let's define this as G0. It's the same. But oops, sorry. Questions? I'm hurrying a little because so that we can finish this, then I can do the, because I have only one lecture. And I'm pretty much sure every step is not very clear. So if you ask me, I can slow down. Okay. So I replace this in here. That's exponential gradient plus omega square over c square 1 times exponential of I omega over c r prime over 4 pi. Again, this is complete. Green's function takes care of everything, but we are interested only in the far field approximation. Right? So in the far field approximation, we can, so the main idea is r minus r prime is nothing but r, and you want a little correction to that. So minus r hat dotted with vector r prime. That's what the contribution is, and we can also replace all the gradients with I times omega over c times r hat, which is what we call ik. With me? So, how my Green's static is this becomes ik, there's a minus, right? So this is minus omega square over c square r hat, two of this coming from here. And that is this minus 1. It's omega square over c square 1. That's a simplification there. And here, oh, no.
Minus omega square c square.
Oh,
The second one.
second one is plus. This is ik, and when I replace this, there is a ikr, and that is denominator just becomes 4 pi r. But there's also this piece remaining, which is nothing but e raised to minus ik dotted with r prime. That's fine overall for this function. But this can be still simplified. This is nothing but our cross product, right? Again, we can see a cross product showing up. So remember your, yeah, so let's think of r hat crossed with r hat crossed with 1. Right, that's equal to r hat. This dotted, that's r hat dotted with 1 minus of 1 times r hat dotted with r hat. That's equal to r hat minus 1. So this way of writing it is nothing but this. So we have minus r hat crossed with r hat crossed with 1 times omega square over c square e raised to ikr over 4 pi r and e raised to minus ik dotted with prime. So we have our Green's function, our Green's dyadic already for use in a sense in the far field approximation. So it's a significant simplicity that you can get immediately. Yes, Krishna.
In the denominator, you have 4 pi r. Is there like, are you saying like the magnitude of r minus r prime
There's a 4 pi there, right?
Yeah, yeah, yeah.
And this is equal to R, right? I can replace this with R minus this.
Uh-huh.
And since it's in the denominator, this is a second order mass.
Right.
Right? When I bring it upstairs, this will not contribute. This will be a higher order. So I can, in the denominator, I need to keep only the leading. Yeah, so that's that. Okay. Good.
Oh, I have one more question.
Yeah.
At what point after introducing Green's dyadic did we go back to our like high equation up there? and stuff?
Oh, we have to now do that. See now,
Okay.
this was our main equation.
Mhm.
So this equation motivates the Green's function.
Right.
So while like I should have gone back right there and constructed the problem, but instead of I just solved it, right? So now we have the Green's function ready. Now we have to go back and put this back in here, right? So this is due to a point chart. I have this whole source sitting. So I have to integrate this. Okay. Okay, so or I can go here. Okay. We have this equation, so let me rewrite that. So I have my Green's dyadic, c square over n square. Yeah, it's a summary kind of. So this is gradient minus 1 del square plus omega square over c square dotted with the Green's dyadic. Just rewriting actually here, nothing. But have everything in one place. And I also have my electric field. This one. Equal to pi dotted with E. That's my total E of electric field. But now let's talk about my incident electric field. So there was this construction of the problem where I had an incident electric field coming in. Incident electric field is the electric field in the absence of the source. If I remove my source, there is no scattered wave. If I remove my scattered wave, whatever is remaining is the incident electric field. So E electric field 0 would be equal to the electric field in when you set chi equal to 0. Okay. The total electric field minus the one that you can't get contribution from the chi equal to 0 is going to be our scattered field. So what is E naught? I just have to set chi equal to 0, right? So this is c square over omega square minus E naught is equal to 0. And the Green's function still obeys that, right? So the Green's dyadic for E naught and E is the same. So if E naught will satisfy this equation, whatever your Green's function equation is, that will satisfy. It's a kind of a trivial one because the right side is 0 in that case. So I can write the C square over omega square times basically repetition, but important, I guess. Oops, this is not. Dotted with not. So now add these two equations. So I have E minus E naught on the left hand side, and the right hand side is simply cut. And that's my scattered electric field. That's E minus E naught. When I get rid of it, maybe I shouldn't call it E0. Yeah, let's just call it E0 or incident if you want. Incident. It's better probably. I don't know what I call it in my notes. Incident is good. Use my Green's function to solve for this E minus E naught. And I have E or omega minus E incident or omega is equal to the Green's dyadic to a spatial integral. So this is gamma R prime, Green's dyadic R comma prime omega dotted with the source, which is chi dotted with E electric field everywhere. So maybe we should clarify this. So this is R prime omega dotted with E R prime. Is that clear? That's pretty much my solution because this I know already. That's my solution. I mean, at least structure is there. So this is the source contribution. That's a scattered piece, and this is your incident piece if I put it on the right side. So our omega is equal to E incident plus, let me substitute this whole thing in here. Notice that all the R dependence can come out of the integral. This is the only R prime dependence in here. R prime dependence is only sitting in here. Exponential is the only R prime dependence in that far field approximation. So this is equal to minus R hat crossed with R hat crossed with 1. 1 means that I have dotted whatever is the next piece, next vector that gets replaced with that. That's there. This is omega square over C square. And there is exponential of IKR over R. And whatever is sitting in here, but now there is a exponential of minus IK vector. And that's your Fourier transform. Notice that Fourier transform exponential shows up, which means that it will be the Fourier transform of the space. Chi R prime omega dotted with exponential IE prime omega. It is still there's a little fishy thing in here. This is not really a solution in the sense that you're solving for the electric field but the electric field is what is causing the chi, right? So that's the cyclic nature of this scattering problem, that this, so this radiates, but that radiation is going to give you a E. So it's a chain reaction, right? In my solution, I need to have all perturbations to get this exactly. But at least to leading approximation, we can say that if I were to put this, so this is a chain, right? So if I put the solution itself inside of this, I'll get an iteration in here. So the first term will be the same as replacing E incident. And then there will be a second term. Keep doing that, you'll get a series out of this. Is that clear? What I'm suggesting? And I will make the approximation that I will keep only the first term. And that's called the Rayleigh approximation. When we say it's a Rayleigh scattering that is contributing to the blue sky, that's an approximation where this is only the first term. What does that mean? When is that allowed? That means that this piece here, there is a volume dependence in there, that is small compared to the wavelength of light. Okay. If the air molecules are small compared to the wavelength of light, so that's how is it? So Rayleigh approximation. Or weak approximation. It's a weak Rayleigh approximation is when you replace E with E incident on the right side. Is that clear? Okay. That immediately replaces this with the E incident, and now I can give it some structure. So let's call this whole thing a scattered electric field, E incident plus E scattered. So E scattered or omega is equal to minus r hat crossed with r hat crossed with 1 times omega square over c square times e raised to I k r, and this is dqr prime exponential minus I k dotted with r prime and E incident now. Only thing I replaced is that I replaced this E with E incident. What is the incident wave? I have a choice on what incident wave is. Let's choose that to be a monochromatic wave. Choose E incident or omega to be equal to E0, a constant, that's the amplitude of the oscillation, times exponential of I k K0, I guess. What should I write? IK R. Yeah, let's call it K incident, right? That is a K incident. So this is the direction of K incident dotted with R prime. So and K incident, let's say, is equal to omega C times R hat incident. So what does that mean? So there is a wave that comes in, right? So that's my K incident. This also decides what is the wavelength of this light. This comes in and it scatters in this direction, and that's your K. That could be angle theta and phi. You can in all directions. Right? That clear the picture? If that is the case,
So the ES is the scattering.
yes. So I just picked the second piece and called it the scattered.
Okay.
This is the incident where total electric field consists of the incident and the scattered. So I call it the scattered.
Oh, I'm sorry.
Yeah.
You said we dropped the chi, because the volume element.
No, I should have cut that. So, messed up. I did not drop that. Should not drop that. Okay. And there is an R prime in there. R prime. This is R prime. Very good. Yeah, so there's an R prime. This is also R prime. And, okay. With all those features in the last minutes. So what I have is scattered electric field is equal to minus R hat crossed with R hat crossed with 1 times omega square over C square K R over R cube R prime with an exponential of, that is a K incident minus, so this is a minus I of vector K minus K incident. It is K minus K incident, right? That's your vector that is showing up, dotted with R prime and I. R prime, omega, only the dotted E naught is there. Okay.
The last time E incident.
E is 0 actually. This is this amplitude alone, right? Exponential, I absorbed it here. So let me take 2 more minutes if you allow me. So let chi be equal to chi itself times 1. Right? That means it's isotropic. So the material is not anisotropic. It doesn't care for X, Y, Z. It's a spherical molecule. It's a very reasonable approximation. Then that one hits this E naught. E naught can come outside, and this will go in here. So then there is a significant simplification. Our omega is equal to minus R hat crossed with R hat crossed with E naught. Omega square over C square E raised to R over R. And this is nothing but the Fourier transform of chi. So this is chi, the Fourier transform of, instead of R prime, now I have K minus K incident and omega. That's it. So if you know the Fourier transform of chi, you get the scattered wave. And you see this omega square over c square. When I square this, that's what will be the radiated power. The intensity will be the square of this. It depends on the 1/4 of lambda square. Right? Scattering is dependent on the frequency. So omega square, so the frequency, higher frequency gets scattered the most. Right? It is linear, so it is scattering, the intensity of scattering is 4th power. The 4th power is very quickly, the blue gets scattered very quickly, and the red gets scattered significantly less after a few scattering. 16:1, for example, after one scatter. So blue dominates too much.
So then what is the actual color of sky? If we see
Oh, white actually. White, yeah. So if you were to have a spectrum of the light that is coming from the sun, it has more blue, but not as much as the sky. It's pretty much white. And after scattering, it is primarily blue.
So our clouds are white.
Why are the clouds white? Good point. So notice there was this approximation here that the air molecules has to be smaller than the wavelength of light if I want to do this approximation. I cannot do this I cannot truncate that series if the molecules are bigger than the wavelength of light. That means if they're not smaller than a micrometer or something. Cloud molecules are bigger. These scattering, approximate Rayleigh scattering doesn't work for them. For that, I have to keep all the series, and that's very hard. But that was done by me. It's called MIE. It's called me scattering. He did this for the whole. You cannot do all these approximations. It's a pretty complicated problem, but at the same time can be done. And then it turns out that it doesn't have as much blue dependence or as much frequency dependence as we have here. So that's where that's why it's white. Yeah, and there is like I would say, when you say that sky is blue because of this, it's one of the reasons. It is not the. It's one of the dominant reasons. Like it is not the only reason. For example, why is the water ocean blue? Again, the same thing. Ocean also behaves in all this way. You can do the same analysis. But is that the dominant one? If there is some algae inside that can dominate. So this is a very good contributor, but if water is perfectly clear, perfectly pure, then that's how you would do it. But water is, especially ocean, would be complicated. A swimming pool is blue probably because of this. You notice a swimming pool typically is blue. It's probably because of the scattering. But often you see beaches have colors of ocean color is not decided completely by the scattering.
So what we are actually viewing is not exactly the exact color of the thing. Because the scattering we see something, you see a different color. Or can you construct the actual color if you see something there? You see swimming pool seems good because of the scattering. So the question is, what is the actual color of the swimming pool?
Yeah. Actual color. Actual color will be, yeah, what do you define by actual color? Like you're saying, without the light, like actual color will be whatever, okay, there is light coming in, let's say red, blue, green. Some of it is absorbed and some of it is reflected. Like whatever is reflected is what we think is the color. For example, when we think of green plant as green, green is not the important factor in it because we see it as green. So it's absorbing everything else. So for cooking, it reads all the other colors. Like that is the reason why you see that plants are sometimes leaves are yellow, right?
Yeah.
Does that mean that those plants cannot cook. The chlorophyll is important for photosynthesis, right?
Yeah.
Can the yellow leaves do photosynthesis? Quiz. What's it?
I think so, because otherwise how can sun?
Yeah, but then you have to explain why. That as the answer, I'm saying, whatever you asked me, that question probably gets answered by that. Like what we see is an interpretation, right? That's the color.
Yeah, I see.
Yeah, sorry for the delay. Yeah, that's significant delay.
Thank you.
Yeah. So think about that. I think that answers your question.